Hey guys, welcome to another episode of Bran Academy. As always, my name is Bran. I'm Mr. Win's twin brother. And today we're talking about chapter 10-7, special segments in a circle. Okay, so the new theorem we're learning today is segments of chords. Okay, so if two chords intersect a circle, so look at this diagram, we have two chords there, then the product of the lengths of the chord segments are equal. Okay, I'm gonna show you a magic trick here, okay? You can use it on your date. So look at this chord here, boom, AC. Let's break it into pieces, okay? So this theorem is saying that AE, the product of the chord segment, AE times EC has to equal the chord of this segment right here, DB. Okay, so DB, we can break that down into DE times EB. Boom, okay? Magic trick. Okay, this is going to be true. How can we prove this trick to be true? Well, we're going to prove it, okay? So still a little throwback here, everyone's favorites. We're going to do a little proof, okay? There's no proof on your tests, okay? Don't worry, but let's get a little throwback, okay? The throwback Monday for you here. Okay, so let's start with this, okay? Our goal is to prove this to be true. Okay, then no matter what type of chord you're doing, like you just do some random chords, like these two chords, boom. Okay, the product of this piece right here and the smaller piece is equal to the other product. Okay, so we're talking about the pieces. Okay, I'm just gonna do this one for us, okay, but please write this all down. Okay, throw back. Angle AED is congruent to angle BEC. Where is that? AED is right here. Boom, BEC. We call those vertical angles. Vertical angles are congruent. Okay, that's step one. Step two. Okay, check this out. Here's a new one. Angle EAD is congruent to angle CBD. Let's find that real quick. Okay. Let's find this, EAD. EAD, okay, this angle, boom, is congruent to CBD, this angle. Ooh, why is that the case? That's interesting. Okay, let's check it out. Okay, let's look here. Right now, what I want to do though, just to make it specific, oh, I should have done this. Connect this triangle, guys. Connect AD real quick. Boom, just connect that. That's the angle it's talking about. And this is kind of a bit harder to see, but just connect BC. So it turns out those two angles share the same arc. Look at this arc that they hit. No way. Okay, CAD, look at that. Boom, hits that arc. CBD, same arc, okay? So if they hit the same arc, they are congruent, okay? This definition is because inscribed angles that intercept the same arc are congruent. Oh, I can't write. Congruent, okay? Now, what do we have here? Okay, we have two triangles. And do we see that the two triangles are similar? Why would they be similar? Okay, we're gonna look at triangle EAD. I cannot write right now. Triangle EAD is similar to triangle EBC, okay? Look at those two triangles. Boom, right here, EAD and then EBC. They are similar, throwback, because of angle similarity, okay? Now, if the triangles are similar, what do we know about their sides? They are in, starts with a P. Starts with a P. They are in proportion. Good, okay? So AE, I'm gonna set this up right here, okay? Over BE equals DE over EC. Reason for this, definition of similar figures, okay? We know that if figures are similar, then the sides are in proportion. Now check out this last step right here. This is the wow step. Step 5, I'm going to cross multiply. Look at this. AE times EC is going to be equal to BE times DE. Reason for this is just the cross product. Or really, you can just put definition of multiplication. Same thing. And boom, look at that beauty. Bam, bam, okay? The same formula that we got with the theorem, okay? And that's the reason why it is true, okay? So no need to memorize this theorem, okay? It's just to prove for us to use this formula, okay? So let's do a couple examples here. Let's do the first example. I'm gonna do the example and number 2, okay? And then you guys will do 1 and 3 on your own. So let's look at this example here. Okay, so we have our chord theorem. Let's call it our chord theorem. So AB, I'm just gonna write this out. AB times what? AB is this piece times BC should equal DB, that piece, times BE. We literally just plug what we have in. 6 times X equals 3 times 8. 6x equals 24. X equals 4. Boom, easy, right? Okay, I'm gonna do number 2 here. All right, let's see what we got. Okay, we know the radius is 7, so we know this other side is 7 as well. But if this piece is 2, that means this right here is 5, okay? So that's good, that is 5. And now, the fact that this is perpendicular, right? We see it's perpendicular here. The fact that this radius or this diameter is perpendicular to the chord, that means it will bisect the chord evenly. So this other half is x as well. So I'm basically going to redraw this to give you a better visual of what we have here. That was supposed to be a perfect circle. But really what we have here is this, okay? Let's try to make it simple for you guys. Boom. X, X. This half over here, this half is actually 12, and over here it's 2. Boom, do we see that? Bam, now we can actually work with this a bit easier. 2 times 12 equals x times x. X squared equals 24. We're going to take the square root. Bam, bam. Let's see, break this down. What we got? Perfect squares. 4 and 6, right? 4 is a perfect square. So take that out as a 2. Bam, that's your final answer. I don't know why my thing's not working. Whoa, that's strange. Try one more time, guys. Okay, there you go. All right, please do 1 and 3 on your own, and then check back with me. So please hit pause right now. All right, guys, so take a look at number 1 here. I should have gave you guys a hint, and then you know that you did need to factor. Okay, so let's kind of break it down step by step. So chord number 1, right, x plus 2 right here. So multiply that together. Then you have 5 times 5. And yeah, you can always just assume if it's a big point in the middle, okay, that's like the center. You FOIL, boom, 5 times 5 is 25. Okay, add like terms to get 4x. Once you get here, hopefully it's familiar, right? Quadratic equation, you want to set it equal to 0, so subtract both sides by 25. And then from here, you need to use your x method to try to factor it out into 2 binomials. So you want to find 2 numbers that multiply to negative 21 and add up to 4. And those 2 numbers are 7 and negative 3. Then once you get to here, you basically set x plus 7 equals 0. So x equals negative 7. And you set x minus 3 equals 0. So x equals 3. So this x equals negative 7, you can always just test it out real quick by plugging it in. But in the end, it's still a negative number, which is why negative 7 will not work. And then 3 will work, so x equals 3. And for number 3, pretty basic, the red line right here. Boom, 2x times 3x. And then blue line, 6 times 5. Boom, boom, little math magic. x is approximately 2.2, right? Round to nearest tenth. And back to problem 2, if we're going to round this, it would be 4.9, I believe. Check that real quick. Yeah, 4.9. Don't put that 0 there. That 0 should not be there. All right. Please check part 2 of chapter 10.7.